Let's work on solving a minimizing maximizing problem. We're finding the extreme of a function using the method of Lagrange multipliers when we have multiple constraints. So the problem statement, we have a plane x plus y plus z is equal to 1, cuts the cylinder x squared plus y squared is equal to 1 into an ellipse, or rather the intersection makes an ellipse. I want to find the points on this ellipse that lie closest and furthest from the origin. So we have multiple constraints here because we are looking for points that minimize and maximize the distance function, but I have to satisfy the plane equation and I have to satisfy the cylinder equation. So let's write down the function that we're trying to minimize. I'm going to call this d tilde. It's going to be a function of x, y, and z, and it gives me the distance of x, y, z, the point, to the origin. Okay, but if I want to minimize this, it's enough to minimize the inside of the square root because the square root is monotonically increasing. So to minimize the square root values, we can just minimize the argument of the square root, what's inside. So I'm going to call my d function x squared plus y squared plus z squared. So we're trying to minimize this. And our multiple constraints are, we have to satisfy the plane and the cylinder. Let's get a picture of what we're going to do. I think this is pretty neat. This describes the geometry of this problem, and we're going to talk about it here in a little bit. But first we have to figure out the math, right? Because the math is going to tell us where we need to draw our vectors. So let's translate everything over to a fresh sheet of paper. All right, that's our cylinder, that's our plane, and this is our distance function that we're trying to minimize. Oops, no, I don't like that. Okay. So let's write down the equations for which these cylinders and these planes are level curves for, right? Because that's how we find normal vectors. And the method of Lagrange is I need to find normal vectors to level curves so I can set them equal to each other, or rather, let's set them parallel to each other. So the cylinder equation, let's say, is x squared plus y squared. And then we're looking at the specific level curve where the cylinder equation returns a 1. All right, for the plane equation, let's say it's p. And let's call it x plus y plus z. And we're looking for the specific level curve of this plane equation when the plane returns a 1. All right, and the distance function, just for completeness, I guess, the distance function for a point x, y, z is x squared plus y squared plus z squared, or rather, I guess I could call this the distance square function. All right, the method of Lagrange says that the gradient of the function that we're trying to minimize or maximize has to be a linear combination of the gradients of the constraint equations. And the geometry is really cool. We're going to talk about it. But let's just go through it and find it now. We'll talk about what the picture is later. The gradient of the distance function would be 2x, 2y, 2z, which now needs to be equal to lambda times the gradient of the cylinder equation, 2x, 2y, and 0, plus a scalar multiple of the plane equation, or rather the gradient of the plane equation, 1, 1, 1. All right, so this is going to open up a system of 3 equations. The equation in the x component, 2x must be equal to 2x lambda plus mu. The y components say that 2y must be 2y lambda plus mu. And the z component says that 2z must be equal to 0 lambda plus mu. All right, let's start with that third equation. It's already solved for mu, so let's replace mu into the second equation and find that 2y is equal to 2y lambda plus 2z. All right, everything has a 2 in it. Let's get rid of that. Y is equal to y lambda plus z. And let's solve this for lambda. So lambda is going to be y minus z over y, or 1 minus z over y. All right, moving to the x. 2x must be equal to 2x lambda plus mu. All right, everything has a 2 in it. Let's get rid of that. X is equal to x. Let's distribute the x. And I've got an x on both sides. 0 is equal to z minus z x y. So 0 is going to be z, or 1 minus x y will be 0, which means that z is 0, or x is equal to y. All right, this is going to open up some cases. So the case when z is equal to 0. We've used the gradient equations to find this, but we haven't used, right? So notice when we got the gradient equations, they were the normal vectors to the constraint equations, the cylinder and the plane, but we didn't use the fact that we want to be specifically on the level curve when I get a 1 from this. So let's use our actual constraint equations. Which one do I want to use? Oh, well, I know information about z, so I don't want to use the cylinder equation. Let's use the plane equation because it has a z in it. X plus y plus z must be 1, right? That's the plane that I have to exist on. Z is equal to 0, x plus y is equal to 1, y is equal to 1 minus x. Cool. Let's use the other equation, the cylinder, that says that x squared plus y squared must be 1. X squared plus y squared must be 1. Let's replace the y. And I'm going to see if I can do this algebra in one step. What's it say? 2x squared, my 1's are gone, minus 2x must be 0. Let's get rid of those 2's and say that x minus 1 times x must be 0. Okay, so x is 0. I think that gives us a point. If x has to be 0, then y must be 1 minus 0, or 1. And this was all under the umbrella that z was 0. If x minus 1 is 0, I get a point where that says x is equal to 1. The y value is going to be 1 minus 1, or 0, and the z value is 0. Okay. This was all under the umbrella that z was equal to 0. Now let's look at the case when x is equal to y. Okay. If x is equal to y, which constraint equation do you want to use? Well, you definitely don't want to use the one that has z's in it because you don't know what z is. Use the cylinder. X squared plus y squared must be 1. If x is equal to y, we could use any substitution that we want. 2y squared must be 1. Y has to be the square root of 2 over 2, plus or minus. Okay. So if that's my y value, what's my x value? Oh, x is equal to that y value. So we have square root 2 over 2, square root 2 over 2. Now the z value can be found. Let's use the plane equation. X plus y plus z has to be 1. If I know my x and my y, I can get my z. So if x is equal to square root 2 over 2, and y is equal to square root 2 over 2, z has to be 1 minus square root 2. Ooh, I don't like that. And you can check if x and y are negative square root 2 over 2, we get 1 plus square root 2. Okay, so if these are the only possible places where I get what I want, where the derivative, or sorry, the gradient of the function I'm trying to minimize or maximize exists in the same plane or satisfies this Lagrange equation, then these are the only possible places where I can have local extrema, or actually any extrema, because we used our conditions of the boundary. So all we need to do is evaluate our distance function at these points. Okay, if you do this, take a minute, see if we get the same thing. All right, I hope my algebra is right. I've got 1, 1, a 1.17 here, roughly. And the distance for this case, I've got roughly 6.83. So I've got a maximum here, and these two give me minimums. They end up being symmetric. So let's look at what just happened. Let me turn everything off, and then we'll turn them on as we talk about them. Oops. Okay, so we have a circular cylinder and a plane that is going to cut that in an ellipse. So we see the ellipse right there. And we're looking at points on this ellipse that minimize or maximize the distance function from the origin. So we've got the distance function. In fact, this isn't the distance function because the distance function exists in 4 dimensions, but this green ball represents level curves to the distance function, right? Everything on the surface of this green ball is the same distance away from the origin. And we're looking for, hold on, let the ball get positive volume again. We're looking for the point where the normal vectors on the green ball are in the right direction when we're on this ellipse. So what do we say? The method of Lagrange told us that we were looking for this equation, where I could write the normal vectors on the distance function, so that green ball, as a linear combination of the normal vectors on my constraint equations. So let's think about what that means. Let's just zoom in. So after we went through that process and we found the points that we were wanting to look at, there were these 4 points, right? A and B are symmetric about the origin. So that was the 1, 0, 0 and the 0, 1, 0. The C was a point that wasn't a minimum or a maximum. And then that D is the maximum. Let's zoom in there. Okay, so the normal vector to the cylinder, oops, sorry, that's the normal vector to the plane, but same thing, right? The normal vector to the plane gives us that direction, and the normal vector to the cylinder gives us that direction. Now I'm looking for the vector that can be written inside the same plane as those two. So those two vectors are going to make a plane, right? Those two vectors generate that plane, and I'm looking for the normal vector on the green ball, the distance function, that lies in that plane. So if we zoomed out there, the normal vector, that's that big vector to the left, that's normal to the distance function. And that normal vector lies in the plane that's generated from the normal vectors of my constraint equations. That's us saying this sentence. Okay, cool. Hope you like this.